Let's solve this carefully from the beginning, because the key idea in this problem is not to guess the missing sides, but to transform the Pythagorean equation into something we can analyze using factors. We have a right triangle, and we know that one of its legs has length 15 units. The other leg and the hypotenuse are unknown, but there is an important condition. All three side lengths must be positive integers. So, our goal is to determine exactly how many such triangles are possible and find all of their side lengths. Let's call the unknown leg x, and let's call the hypotenuse y. Since this is a right triangle, we can immediately use the Pythagorean theorem. Remember, the Pythagorean theorem says that for a right triangle, the square of one leg plus the square of the other leg equals the square of the hypotenuse. So here, we write 15 squared plus x squared equals y squared. Now, 15 squared is 15 multiplied by 15, which gives 225. Therefore, our equation becomes 225 plus x squared equals y squared. Now let's rearrange this equation. We want to isolate the constant 225 on one side. So subtract x squared from both sides. That gives us 225 equals y squared minus x squared. And this is where we get the important mathematical opportunity. Notice that the right-hand side is a difference of two squares. There is a standard identity that says the difference between two squares can be factored as the first quantity plus the second quantity, multiplied by the first quantity minus the second quantity. So y squared minus x squared becomes the quantity y plus x, multiplied by the quantity y minus x. Therefore, we have the equation. The quantity y plus x multiplied by the quantity y minus x equals 225. Now pause here and notice why this transformation is so useful. We started with a problem involving unknown triangle sides, but now we have turned it into a problem about factor pairs of 225. We also know something about the relationship between x and y. Since y is the hypotenuse, it must be longer than the other leg x. In other words, y is greater than x. Because both x and y are positive integers, the quantity y plus x is a positive integer, and the quantity y minus x is also a positive integer. So now our task is simply to find all the positive factor pairs of 225. Let's list them carefully. 225 multiplied by 1 gives 225. So one factor pair is 225 and 1. 75 multiplied by 3 gives 225. So another pair is 75 and 3. 45 multiplied by 5 gives 225, giving 45 and 5. 25 multiplied by 9 gives 225. Giving 25 and 9. And finally, 15 multiplied by 15 gives 225. So 15 and 15 is also a factor pair. But we have to be careful here. The two factors represent y plus x and y minus x. Since x is positive, y plus x must be greater than y minus x. So the pair 15 and 15 cannot possibly work because those two quantities would be equal. which would force x to be 0. But x has to be a positive integer. Therefore, we discard the pair 15 and 15. That leaves us with 4 possible factor pairs, and we need to test each one. Let's start with the largest factor pair, 225 and 1. Suppose y plus x equals 225 and y minus x equals 1. Now we want to find y and x. A very convenient thing to do is add these two equations together. On the left, we have y plus y minus x. The positive x and negative x cancel each other, leaving 2y. On the right, we have 225 plus 1, which equals 226. So, we get 2y equals 226. Divide both sides by 2, and we obtain y equals 113. Now, we substitute this value back into one of our original equations. Let's use y minus x equals 1. Replacing y with 113 gives 113 minus x equals 1. To find x, subtract 113 from both sides, or equivalently, recognize that x must be 112. So, x equals 112. Therefore, our first triangle has side lengths 15, 112, and 113. Let's quickly verify that this really works. 15 squared is 225. 112 squared is 12,544. Add those together and we get 12,769. 113 squared is also 12,769. So the Pythagorean theorem checks out. That gives us our first valid triangle. If you're following along, this is a good point to pause the video and see whether you can predict the remaining triangles before we continue. And if you're enjoying this type of integer geometry problem, remember to like the video and subscribe for more problems like this. Now let's move to the second factor pair, 75 and 3. We suppose that y plus x equals 75, while y minus x equals 3. Again, notice that the same structure appears. If we add these two equations, the x terms cancel. We get 2y equals 75 plus 3, which is 78. Divide both sides by 2, and we get y equals 39. Now, substitute 39 for y into the equation y minus x equals 3. This gives us 39 minus x equals 3. Therefore, x must equal 36, because 39 minus 36 is 3. So, the second triangle has side lengths 15, 36, and 39. We can check it as well. 15 squared is 225, and 36 squared is 1,296. Adding them gives 1,521. And 39 squared is also 1,521. So this triangle is valid. Now, let's move to the third factor pair, 45 and 5. This time we have y plus x equals 45 and y minus x equals 5. Add these equations together. Again, x cancels with negative x, leaving 2y. On the other side, 45 plus 5 equals 50. So 2y equals 50. Divide by 2, and we get y equals 25. Now, substitute 25 into y minus x equals 5. That gives 25 minus x equals 5. Therefore, x equals 20 because 25 minus 20 is 5. So our third triangle has side lengths 15, 20, and 25. This is a familiar Pythagorean triple, and we can verify it quickly. 15 squared is 225, 20 squared is 400, and their sum is 625. 25 squared is also 625, so everything checks perfectly. Now we have one final factor pair to examine, namely 25 and 9. Suppose y plus x equals 25 and y minus x equals 9. Add these two equations just as before. The x terms cancel, leaving 2y. On the other side, 25 plus 9 equals 34. Therefore, 2y equals 34. Divide both sides by 2, and we get y equals 17. Now substitute 17 into y minus x equals 9. We get 17 minus x equals 9. Therefore, x equals 8, because 17 minus 8 equals 9. So this gives us another valid triangle with side lengths 8, 15, and 17. Notice something interesting here. The known leg was 15, but when we list the sides in increasing order, this triangle is 8, 15, and 17. That is completely fine because 15 is still one of the legs, while 17 is the hypotenuse. So, this fourth case works as well. Therefore, after checking every possible factor pair, we have found exactly 4 different right triangles whose side lengths are positive integers, and one of the legs has length 15. The 4 triangles are 8, 15, and 17, 15, 20, and 25, 15, 36, and 39, and 15, 112, and 113. Every one of these satisfies the Pythagorean theorem, and every side length is a positive integer. Now let's step back and identify the main trick, because this is the part I really want you to remember. We did not have to randomly search for possible values of x and y. We started with the Pythagorean theorem, 15 squared plus x squared equals y squared. We simplified 15 squared to 225. Rearranged to get 225 equals y squared minus x squared, and then recognize the difference of 2 squares. That allowed us to write the equation as the quantity y plus x multiplied by the quantity y minus x equals 225. Once we reached that form, the geometry problem became a factor pair problem. Each factor pair gave us a possible system of 2 simple equations, and adding those equations immediately canceled x and allowed us to find y. Then we substituted back to find x. So, whenever you see a right triangle problem where one side is known and the remaining sides are required to be integers, don't immediately start guessing numbers. First, write the Pythagorean theorem and look for a difference of squares. That algebraic transformation can reduce a seemingly difficult search to a short list of factor pairs. And in this problem, that single idea reveals all 4 solutions, 8, 15, 17, 15, 20, 25, 15, 36, 39, and 15, 112, 113. If you found all 4 before the end, let me know in the comments, And don't forget to like and subscribe for more challenging math problems.